All right, welcome. In this video, I'm going to be reviewing Calculus BC Unit 11, the unit about series of constants, before we get in and really get going on our Taylor series. So I'm going to show you what we studied in my class. Okay, we started with the concept of an infinite series at all. What does that mean? Series notation. I don't assume that people have seen the series before they get to my class, because oftentimes they have not. The definition of what it means for a series to converge. The divergence test, also known as the nth term test. I'm going to put that in there. Okay. Geometric series. We talked about some telescoping series, but I'm not going to talk about that in this video because that is not an AP Calculus topic. Okay, and then we did a bunch of examples. Okay, and if you need more on 11.1 or you're unsure of any of these things, I bet you could click right about here and I'd have a link for you to take you to the lesson. Okay, for 11.2, test for convergence. The direct comparison test, integral test, p-series test, harmonic series, limit comparison test. I'll go over all of those in this video, but if you needed the really detailed video, again, you could probably click up here and I'm going to put the link in there. Okay, 11.3 was alternating series. Okay, alternating series test, alternating series error bound, the alternating harmonic series, the difference between conditional and absolute convergence, and a bunch of examples. Okay. And then in 11.4, we studied the ratio test. Oh, pardon me, if you need more detail on 11.3, click up there. Okay, 11.4, ratio test for absolute convergence. We looked at some power series. We talked about interval and radius of convergence, and we did a bunch of examples, but that's not going to be the emphasis on this unit's exam. Okay, the interval and radius of convergence, I have plenty of those questions I'm going to ask you about Taylor series and Maclaurin series in the next unit, and we'll keep practicing that, but that's probably not something you're going to see on our test. Now, if you don't know the ratio test or you don't know any of these things, well, again, I'm going to link the video for that right there. Okay. All right. Infinite series, 11.1. What did we start with? We started with the series notation, but I'm not going to go in and tell you about the anatomy of a series and the sigma operator and where it starts and ends. That's you already know that. Okay? And if you don't, then you need to go back and watch something other than the entire unit recap, right? Definition of convergence. Let me copy that in real quick. All right, so the idea was if the limit of the partial sums existed, then the series converged. Okay, and the partial sums is what I get by adding up a finite number of terms. And so like if there's a formula for the, a total after adding up n terms and the limit of that formula exists, that's what it means to converge. Okay, that's one of two ways that we know how to actually find the value a series converges to is when we're formula for Sn and we just take the limit of it. And the other situation is the geometric series. And I think that's just what I'm going to talk about right now. Yeah. Okay. So for a geometric series, we need to be able to recognize when a series is geometric. Okay. We need to we need to know that geometric series they look exponential in n. So this would be, sometimes they have something multiplied by them. So I could say this is as n runs from 1 to infinity of some number times some other number to the nth power. That's the general, geometric scenario. And we can say that this one, we need to know that one converges when the absolute value of r is less than 1, and it diverges when the absolute value of r is greater than or equal to 1. Okay? And if the series converges, maybe I'll just stay using black. If the series converges, and because the absolute value of r is less than 1, well, then it's going to be the case that the total it adds up to is given by the first term, whatever that is, whether we're starting at n equals 1 or n equals 0 or n equals 15. We just plug in whatever we start with to get our first term, and then we would multiply by 1 over 1 minus r. So we'll do a quick example of that. So, for example, let's look at the sum as n runs from. I'll make this one, I don't know, maybe a little different. Maybe 3 to infinity of 5/4 times 1/2 to the n. It's like, which of these is the ratio, or which of these, well, which piece is which? Okay, so I know that r is the ratio is the number that's getting taken to the nth power. Okay, so I'm going to say r equals 1/2. Okay, the absolute value of r is less than 1 tells me that the series converges. But with a geometric series, they oftentimes are asking you, like, what value does the thing converge to? And I think that this is converging to a total of, first term would be where n equals 3, so 5/4 times 1/8, so 5/32, times 1/1 minus r is 1/2. Okay. And 1 minus 1/2 is 1/2, so it'd be like multiplying by 2, and that's going to end up being 10/32, or 5/16, however you like it. Okay, that's the geometric series scenario. Okay, I also need to remind you about the divergence test, right? And we know that the divergence test is that if the limit of the terms of a series is not 0, that series is for sure diverging. Okay, so here I've got enough room. If the limit of an is not equal to 0 as n goes to infinity, then it must be the case that the sum as n runs from 1 to infinity, or really any number to infinity, of an diverges. Okay, that's the divergence test. Also known, and I'll probably say that again, also known as the nth term test, or the nth term test for divergence. Okay. And I think that's all I've got to say about 11.1. Okay. 11.2 was all of the different tests. And so let's, 11.2, that was convergence tests. Okay. All right, the direct comparison test. I'm going to copy in, to speed this up, just copy in the rule. All right, so the principle of direct comparison is that if you have terms that are bigger than the terms of a divergent series, then your series definitely is going to diverge. Okay, and if you have terms that are smaller than the terms of a convergent sequence, of a convergent series, then you're going to converge as well. And I might be, going past a few details, like what if an was really negative and bn, was positive. I mean, assuming that we're talking about sizes of terms here, it's going to be true. Another way you can think about this is if you're bigger than infinity, you're infinity, and if you're smaller than a number that's finite, you're finite. Okay, so that's direct comparison. We used that to prove the integral test, which I'm going to copy here, right? All right, and the integral test says that if you've got a function that's continuous and positive and decreasing, and its improper integral converges, then the related series is going to also converge. And if that improper integral diverges, then the related series is also going to diverge. Okay, this is a really good test, but actually going in and computing these integrals is not that likely. What you also need to know about this scenario is that when they converge, so if, suppose the sum from 1 to infinity of f of n and the integral from 1 to infinity of f of x dx both converge, and f is a continuous and positive and decreasing function, all the conditions are met, then the series is greater. So I did, that's another thing that, and, got reasoning why that's the case, kind of all over the place. Even the proof of the integral test kind of goes to why the series is bigger. And that's going to be the integral test. Okay, the next one is the p-series test. And I don't think I need to pause. This won't take too long to write. Okay, p-series test. Okay? First, you need to know what is a p-series, right? P-series has a 1 in the numerator and a power of n in the denominator. Anything else, it's not a p-series, right? If you have n to the p plus n to the q or something, not a p-series. Okay? This is a p-series. This converges when p is bigger than 1. And this diverges when p is less than or equal to 1. When p is equal to 1, that's the sum of 1 over n. That's 1 plus a half plus a third plus a fourth plus a fifth. That's the harmonic series, and you know that diverges, okay? So I'm not even going to spend time on that, right? Because we all agree the harmonic series diverges. I proved it for you a variety of ways this unit, and I think, we're just going to move on to the limit comparison test. Okay? That's one I'm going to also copy just real quick. All right, there it is. So it kind of got a little crowded, and so I just zoomed out. But if we've got, and this is not for alternating series, is what this is saying. If we've got two sequences of positive terms, and the limit of their ratio is positive and finite, then the corresponding series have the same convergence-divergence behavior. And this is most useful for ones that are not quite a p-series, but they look a whole lot like one, and we just know. Like, for instance, I'll do a quick example for us. Sum from n equals 3 to infinity of n plus 2 over, n to the 5th plus 7n. Something like that. Okay? We know this is going to converge because it's bigger on bottom by 4, but that's not going to be our reason. Bigger on bottom by 4, that's not very specific, and it doesn't have anything to do with any of the theorems that we have in this class, right? So I know that it's related to 1 over n to the 4. So I'm going to do limit comparison against 1 over n to the 4, and how I'm going to justify my answer is I'm going to start off by saying, okay, my one that I want to compare it with is the sum from 3 to infinity of 1 over n to the 4. What does that do? That converges. Why does it converge? The p-series test. Okay. P is equal to 4, which is greater than 1. Okay. Then, after that, I compute the limit of the ratio. Okay, that's the limit as n approaches infinity of n plus 2 over n to the 5 plus 7 divided by 1 over n to the 4 is like multiplied by n to the 4 over 1. That limit is 1. Okay. Because it's positive and finite, I'm going to express that. Right, those are the conditions. And finite. Therefore, I'm going to say, so the sum from 3 to infinity also, pardon me, I've gotten ahead of myself, and I've lost my eraser. There it is. The sum from 3 to infinity of n plus 2 divided by n to the 5 plus 7 is going to also converge. And that was an example of limit comparison test. Okay, I'm not really sure if that was covered up while I was writing. I don't know if I was off the shot, or if that was still in. I don't know, but I just wanted you to be able to see it. Okay, let's move on to 11.3. Right, in 11.3 we studied alternating series, and an alternating series is the one that goes plus, minus, right? And things that cause a series to be alternating is like a -1 to the n in the numerator, or maybe a cosine of pi n. Those are how we know we're looking at an alternating series. And we have a test to determine if an alternating series is converging. Okay, I'm going to copy that in right now. All right, had a pen issue. It ran out of ink suddenly. But if we've got a series that's alternating, whose terms are decreasing in size or magnitude, and the limit of their terms is 0, that means converging. Okay, and that's the alternating series test, right? Alternating series, we learned that they can converge 2 different ways, right? And so I'm going to kind of go into that. Okay, so if we have a convergent alternating series that diverges when we take away the negatives, right? If we take the absolute value of the terms and now the series diverges, that's conditional conversion. A good example of this is the alternating harmonic series, the n over the square root of n. Okay, these kind of p-series ones. That's conditionally convergent. Okay, that means that the value that it converges to is conditioned upon the ordering of the terms, but we don't really need to worry about that. Okay, if we see a convergent alternating series and we take the absolute value of the terms and it still converges, that's what we call absolutely convergent because, well, we took the absolute value of the terms and it still converged. Okay, so we need to know the difference between those two things. An example of this would be -1 to the n over n factorial, or -1 to the n over n to the 6th power, or something, something that would converge without the alternating part. Okay? The error bound, okay, for that, I think what you need to know is for an alternating series, the error is no more than the absolute value of the next term. So if we approximated the value of a converging alternating series we use 10 terms, the absolute value of the 11th term will be our error bound. Okay? And yeah, let's move on to 11.4. All right, the ratio test. So what you do is you take the limit of the ratio of successive terms, or I guess the absolute value of the ratio of successive terms. Suppose that comes back L. If L is less than 1, then your series converges absolutely. If L is greater than 1, then you know with certainty that your series diverges. But if L equals 1, it's probably the case that you tried to use the ratio test on a p-series, or something that you should have used the limit comparison test on against a p-series, and that's going to be, you used the wrong test, okay? Don't do that. What you want to use the ratio test for is like a mix of things like n squared over 3 to the n. Okay, that's power and exponential, so you can use both of them, or you can't use two different tests at the same time and just use the ratio test. Also, anything with factorial in it, you're going to want to use the ratio test for. Okay, but actually executing the ratio test is pretty straightforward. We were really good at that. It's using it to determine the interval of convergence that is a situation for us. So I'm going to set up our scenario here. Okay. With a power series, some from 0 to infinity of some kind of expression in terms of n with some x's in it, we can use the ratio test to determine what values of x make this thing converge. And we start there. And now the whole full-blown ratio test for interval of convergence problems are not something that I'm testing on my unit 11, but we'll do it a lot in the next unit. What you need to know is that a power series is centered at x equals c. It will always converge when x equals c, right? This little x-axis. Okay, when x equals c, I've got 0 to the nth power. Every time a 0. So regardless of what an is, you're adding up a bunch of zeros, and that converges to 0. So it always here. And now the radius can be 0, and it can be infinity, but for the most part, most of these that we deal with in AP Calculus, there's like a finite radius, right? And we would call that our radius of convergence, r. Okay? And this would be an end point here. Okay? Now, on the interior of the interval of convergence, I'm hoping that was about the same length. Yeah, that's good enough. Okay, we know that the series converges absolutely. Okay, and over here too, right where it's jagged. On the outsides, I know that the series diverges. So I'll just put like, I don't know, right here. Now, at the endpoints, we don't really know. It can go either way. Okay? Not sure what's going to happen. It can converge absolutely there. It can diverge. It can converge conditionally. But converges conditionally only happens at an endpoint of the interval of convergence. So if you are told that you have conditional convergence at a place, you know what the edge of the interval is. You always know what it's centered at because it's it's x minus c to the n. If it's just x to the n, you know it's centered at 0. And so that can give you the radius, and you can find some other stuff out. Okay, I've got a bunch of practice problems on that, and I would definitely recommend them. I think it's my online quiz, which says just Unit 11 extra practice or Unit 11 review ungraded or something like that. There's going to be a bunch of that type of question in there. I think I've gone through all of the tests for convergence. I've talked about absolute and conditional convergence. We've done all of the different tests for series that we need to do for AP Calculus. That's all I got to tell you about. Thanks for watching.